atoms, and then neutrons are the other ones. Memorize these numbers, 1.007825 and 1.008665 for that, right? And then you'll eventually want to memorize like the alpha particle one, but there it is, right? So let's figure out a binding energy just for fun, okay? So let's do for carbon-12, we'll find the binding energy of carbon-12, which is the easiest one to do.
About a hydrogen one.
No, das Telefon klingelt. Klingt, das Telefon klingt. The telephone sounds literally, right? Okay, so what we're going to do is we're going to take apart a carbon atom, right? And we're going to take carbon-12 and we're going to turn it into 6 hydrogen atoms, right? And 6 neutrons. Yeah, that's we're just going to take it apart into those pieces, right? And that's what it's made out of, correct? We could do that. That's 6 electrons, 6 protons, 6 neutrons. And that's the definition, okay? And so when we do that, basically the mass that we get is 6 times 1.007825, right? And this is the hydrogen atoms, isn't it? Yeah? Okay. And then we go 6 times 1.008665, right? And then we're going to add this up, right? The taken apart mass is 6 times plus 6 times 1.008665. Okay, and I'm getting that it's 12, and don't round these guys because we know these are our sig figs, right? 12.9894. These are the sig figs, right? When we subtract 12 from this is what we've got. Don't round that to like 12.09 or something like that, or 12.10. No rounding. Don't round. Okay. So this is this. Do you see that that's more mass than the neutral atom? What's the mass of a neutral carbon atom? Exactly 12. So we take away the neutral atom mass, right? Right. It's like as many zeros as we care to put on there. It's exactly 12, right? So minus 12. Whoops. Minus 12. 0.09894, and that's the difference in mass times 931.5. And this is MeV per U. That's how many million electron volts of energy there is per atomic mass unit. So multiply by 931.5. We still have 4 sig figs. This is 4 sig figs. That's 4 sig figs, not 5, because leading zeros don't count. And this is 92.16 MeV, right? This is the binding energy. Literally what that means is that's the energy it would take to take a carbon atom and, through some act of God, turn it into 6 hydrogen atoms, 6 neutrons. Yeah? It's not something that naturally happens. It's just a definition. It's an arbitrary thing. Yeah? This is H6. This is the atomic notation of hydrogen.
Oh, okay.
That's a 1. These are 1s. How's that? 6 1s. Because there's other kinds of hydrogen, right? There's 2-1 hydrogen. There's 3-1 hydrogen, right? Okay. Now, the other thing that we talk about too with this thing, if it's 92.16, right? We could also go 92.16 divided by 12, right? So I'm going to divide this guy by 12, and this is the binding energy per nucleon, 7.680 MeV per nucleon. If they say binding energy, they want the whole thing. If they say per nucleon, then they want you to divide by the atomic mass number, which in this case is 12. The reason why you do per nucleon is simply because very large atoms like uranium are tightly bound. Right? But they have a buttload of binding energy just because they have a buttload of nucleons. So to compare the stability of carbon to the stability of uranium-235, you have to talk about it per nucleon. Yeah? In the same way, it's meaningless to say something like there's more people unemployed in the U.S. than are working in Canada. There's also more people unemployed in the U.S. than are working in Burundi too, right? You know, so you have to talk about per capita, yeah? All right. You guys ready to try this?
Yeah, we are.
Yeah, you are. So in general, by the way, if a process gains energy, or I'm sorry, if a process gains mass, if from the left side of the thing to the right side, if this has more mass, then the thing requires energy to do. In spontaneous nuclear reactions like radioactive decays, this side has less energy, which means, or less mass, which means that energy is released. Okay? So in this case, this side has more mass. That means it required the energy. If you lose mass, the question is, where does the mass go? It goes to energy. Let's have you guys. Oh, let me show you one last thing here. Look up the neutral atoms. On page 1064, you will find the table. They've got selected isotopes, right? I'll show you where this is. So at home, if you want to get the answers that they have in the book, you better use their masses, which are frozen in time in 1997 or something like that. So here they are. I'm in the table right here. Let's zoom out a little bit. Okay. But this is page 1064, and you can see some of these masses. Like there's carbon 12 is exactly 12, that because there it is, duh, right? They should just say, you tell me, or something like that, right? But there they are. Helium atom, we're actually going to use this to represent an alpha particle, the 4.00. Say it again. You want to go to page 1064, but let me show you something even cooler than that. Okay. Yeah, you can find it on a website. So let me just show you. And by the way, back in my day when I was in college, okay, we had this book about this thick that had all the energies and all of the masses of the nuclei and stuff like that. It was a giant book. Now it is, apparently it's this website in South Korea. I hope it's South Korea. There we go. Right. So it is, if you click on links, and I can't even find the links on my... On the top, there it is. Okay. If you go here, it's this guy right here. Is it .kr? Is that South Korea? I don't know. But there it is. This is our chart of the nuclides. My chart is over there on the wall, frozen at some point in time, and it's all sliced up because this is a very long, narrow, sort of like squashed banana-looking thing, right? But there it is over there. See it on the wall? Right, but it's been cut so that it fits on a rectangular sheet of paper. Okay, and the axes are, this way is atomic number, this way is atomic mass, mass number this way, atomic number this way, and so you can click on these things, right? You can go in here. Here are all the ones we're talking about. Here's carbon 12, which is, of course, if I click on it, carbon 12 is the one that's exactly 12, right? Okay, but we can go in here. Carbon 14 is right there. And carbon 14 apparently beta decays. It turns into nitrogen. Is that right? Yeah, to nitrogen 14. And then, of course, you can click on that and see what nitrogen is and see where all these decays take you. But there's the mass right there. And then they give you the uncertainty, which they're not very uncertain about that, are they? Right. You can also, if you want to go to something, you can go uranium-235, and hey, you're there. Right? And then look at alpha decays to thorium. Thorium beta decays to palladium. That alpha decays. Oh my gosh, it's like a little voyage there. But anyway, it's a very cool thing. And then if you want to go up in the table, you can go up like that. So you can use either one. If you use these values, understand you're going to get something slightly different from what's in the book because they measure them more and more and more accurately. So. Okay, let's go.
Does very short mean they just like disappear?
A very short half-life. Very short means that it's just nobody's been able to measure it yet. Yeah, it's just like. Okay, let's try. Okay, so nitrogen 13, the binding energy of nitrogen 13. Now nitrogen is atom number 7. So how many neutrons do we have? 6 of those, right? So the mass here is going to be 7 of those, 6 of these. Right? And then the neutral atom mass is not 13, it's actually 13.0